You use satellites for an application which is a bit unusual. Tell me about how you track animals using satellites.
We track animals various ways, but usually we put on their back or some places the little tracking device. We call them beacon or tags, and it is being used for, well, my field is marine animals, and we use them both for fishes, which never come back to the surface to breathe, or for marine mammals or sea turtles who come back to the surface to breathe. So for the air breathing animals, the way we track them is rather easy, because once the animal is at the surface, there will be the signal from the beacon will be sent to the satellites, and that's the way the animal will be located. For the non-air breathing animals, so the fishes, the problem is a bit different, and we have to use more elaborate ways of tracking them. And we use mostly light-based geolocation. So the whole idea is we're recording on both, and this is different beacon. It's, this is typical, the two types of beacons that we are using to tag animals like tunas. And so it's being, there is a leech and then an anchor, and it's being put in the animal, and the animal drags it.
So if I was a fish swimming like this, that's sitting,
it's sitting
like that.
Like this. It's being attached there, and there is a little thing that keeps it close to the animal.
So I can
and
swim
then
around like
it
this.
swims, and then it breaks there, and then it slips away from here, and then comes back to the surface and pops out. And we get the measurements. Then once the satellite when the tag pops out, it transmits its information from the satellite.
So the problem here is that the satellites use the electromagnetic spectrum, and those signals, light, basically doesn't travel underwater.
Yeah.
And so if an animal is going to come back up and breathe, the little tag pops up.
Then you have
and you're right.
an electromagnetic signal that tells you. But for those animals that do not come for breeding, you get the information only when the tag breaks out away from the animals and pops up.
So the tag knows where it is, and it saves the data and saves the data.
It doesn't know where it is. Actually, it records the light. So the amount of solar light that is at the depth of the animal, and it also records the pressure, so the depth, and we can correct for the depth effect on the light, and basically what we infer from those measurements is the sunrise and sunset time.
Right.
So for each day we have recordings that tell us where the animal was, the sunrise at this hour and set at this hour. And in theory, you can show actually that there are only two places on Earth that have the same sunrise and sunset time. And basically, or intuitively, when you get sunrise and sunset time established, you can easily compute noon time, and noon time gives you the longitude.
So it's like a detective puzzle. You've got all these pieces to put together.
And the length of the day is proportional to the latitude. And so you get the position.
Clever. Yeah, it's very clever. So you're sitting here in CLS, and you've got these tags on animals out somewhere in the ocean, and you get these little packets of data back, which tell you where the animals are or where they've been. What can you do with that information?
Basically, the whole story is to be able to know to determine the migration routes of the animals, and tell also their foraging areas. Most of the animals that are being tracked are endangered species, or exploited or even overexploited species. And the whole purpose of this for the biologists is to know better the biology of these animals, and most of all, to know the habitats that they occupy, so that we can eventually protect them. That's the main purpose of the tracking experiments.
On land, we think of habitats as being a forest, and the forest stays here, and you know where your forest is, and that's where you go to find an animal. But in the ocean, those habitats are moving around.
Exactly. So when you track a sufficient number of animals, you will see that they will go to places that are indeed moving, because everything is moving in the ocean. But then you realize that those guys are going to places where they find appropriate conditions for surviving. That is for fishes, or for most places where there is the right temperature, because every fish has its prefers what we call thermal preferendum, so the range of temperature where he prefers to sit, and they need to find food also. So basically, and each animal has its preferred food type of food, and given the size also, they need more or less food. So basically, once we have tracked a number of animals and we can superimpose the trajectories over information provided by the satellites also, like sea surface temperature maps or primary production or ocean chlorophyll data. And so we just correlate the trajectories with what we know about the ocean, and we define the physical characteristics of the preferred habitats of the animal. So that's once we are done with the tracking experiments, we still can say this place with that temperature and that amount of chlorophyll is favorable to the presence of this animal. And of course, those areas are moving, but the satellites are there every day to tell us where those preferred temperatures or those preferred amounts of chlorophyll are.
Once you know where the habitat is moving, how can you alter the behavior of humans, perhaps, to make use of that data?
Yeah, I mean, that's an interesting question, and it's been used in practice in the US, for example, where there was a big problem. Well, there is a problem of bycatch of sea turtles by longliners, namely in the area of Hawaii, where longliners are targeting swordfish and tuna are catching sea turtles. And there are rules now to avoid, setting quotas on the maximum number of turtles that this fleet can catch. And so scientists have tracked those turtles to begin with to determine actually their habitats, and they found that the main characteristic of the habitat was the temperature. So there is now a website called Turtle Watch where they're actually mapping the range of temperature where the sea turtles are found to let the fishermen know that these are areas with high risk of catches of sea turtles. And the same has been done for swordfishes. We know where areas where the swordfish prefer to go, and so there are even information from NOAA actually in the United States telling people where there are high chances of capturing swordfish without capturing sea turtles.
So there are these different habitats in the ocean, and actually they may overlap and they may not, because different species
overlap. They overlap in most places, a lot of places, because all animals are going for food, and food is always at the same place. But there are places where you can actually separate habitats, and these are the places where you should go to minimize bycatches.
So you can actually tell the humans not to go fishing here because that's where the turtles are, but there might be swordfish over here.
At least you can tell them if you go there is a maximum risk of catching tuna, and the law is that if you catch more than 20 or 25 tuna during a season, your season is finished. So they're doing everything they can to avoid this.
So all of this satellite information is it's directly helping fisheries and countries plan policies.
Yeah, and minimizing bycatches.
How long does one of these beacons last? How long does the battery last?
It depends, but typically for the underwater, so the underwater tags, typically we have tagging between 6 months, 1 year maximum.
So it's a long time.
It's a long time, and for air breeding animals, there are some possibly lasting 2 years.
So every time, in the case of the turtles, they breathe air, so they're coming up to the surface. Every time the little antenna pops up,
they're transmitting their position.
Calls home. And does it send other information as well?
Yes, it's also depending on the tags. There are there are simple or elaborate tags. The more elaborate ones are transmitting information like the water temperature, the depth through the pressure measurements. We have no chlorophyll sensor, fluorometers that are transmitting information. This is for the larger animals. We have these on large turtles or seals or sea lions and things like that, or elephant seals. There are even animals on which we have magnetometers to measure the Earth's magnetic field that they're feeling. And we have light sensors, as I said. What else? Accelerometers. No, there are for some animals we are even able to reconstruct in 3 dimensions the dives. For example, for elephant seals, people have been able to monitor the fact that elephant seals actually they dive quite deep, and apparently they fall asleep.
That's brilliant.
They fall asleep, and when they fall asleep, actually they change orientation. Their belly is coming up.
They lie
down. And actually it's just because they no longer control what's going on, so they fall asleep. No, and simply buoyancy is that the belly is lighter than the backbone is taking them this way. I mean,
right.
It's just in the isostatic position, and then all of a sudden they wake up and then they turn return and they come back.
And all of that data is relayed via satellites, and that's why the satellites are important. It's because they can collect that data from wherever it's being transmitted and bring it back to one central point.
Most of those data are transmitted by satellite, or for some animals like elephant seals or animals that are coming back to the same places. There can be large memories on the tags, and then the information can be retrieved when the animals come back to the beach, where the people, actually the scientists, take the tag back, and then they just get everything that is in the memory.
Satellite technology requires all these different types of expertise. You can look at so many things, but you also need lots of different types of people to do that work.
Yeah, it's incredibly collaborative and multidisciplinary sciences, and for the moment, actually, I'm mostly working with sea turtles, but the big stuff about sea turtles, to understand what's going on, is a combination of satellite tracking to tell us about the trajectories, the habitat, genetics to understand how the population mixes, and modeling to understand, actually, to try to put into models the behavior of the animals and try to guess how the population will evolve about all this. So it's a lot of mathematics, genetics, biology. I'm a physical oceanographer to begin with, and my story with animal began a day where a biologist came in my office showing me trajectories of leatherback turtles that they were tracking from French Guiana to Canada and Newfoundland, and they couldn't make sense of the trajectories, and they asked me if as an oceanographer I could tell them something about the trajectory, and I said yes, clearly you can see the trace of different currents. You could see the leatherback going through the Gulf Stream and being kicked off by the Gulf Stream, and then circulating through the Atlantic with the North Atlantic current, trying to coming back west and being hit again by the Azores currents and that. And there were clear signatures of the effect of the currents. And I found that very interesting, and the biologists too. So we started collaborating, and the year after we started collaborating, we got a paper in Nature. So I said, wow,
That'll do.
that's great.